Hello, welcome to our lecture. Let me introduce you our paper, Generalization and Memorization, the Bias Potential Model. The focus of our paper is on the analysis of distribution learning models. The task of distribution learning is to estimate an unknown probability distribution. These broad subjects includes density estimation and generative modeling. One of the most important issues of distribution learning is to understand these models' generalization ability, namely how they are able to recover a distribution so well given so few samples. In particular, we need to explain how these models manage to overcome issues like memorization and the curse of dimensionality. In our paper, we focus on a particular density estimation model called the bias potential model. To begin with, let me talk about what difficulties we are facing. For the notation, let Q star be the target distribution. Let Q star n be the empirical distribution associated with n points, with n sample points. So one obstacle to generalization is the curse of dimensionality. Let's consider the empirical distribution and measure its generalization error by the Wasserstein metric. Then we have that in general, this error scales as n to the power of -1 over d. Therefore, the sample complexity becomes exponential in the dimension d. The relevance is that a model without a proper inductive bias cannot perform better than this rate and would also suffer from the curse of dimensionality. The second difficulty is memorization. If the model has sufficient capacity, then the unique minimizer of its loss will simply be the empirical distribution. Thus, if the model converges successfully, it will simply converge to this empirical distribution. Effectively, the model memorizes the samples and becomes trivial. Our goal is to close the gap between this theoretical worst case and the practical success of distribution learning. So in particular, we need to show that these models can achieve a dimension-independent generalization error so that the sample complexity becomes practical. Heuristically, those models lie between two extremes. One extreme are models without any inductive bias, such as histograms, which are vulnerable to memorization. The other extreme are models with very strong inductive bias, such as the Gaussian family, which are too restrictive. A good model needs to satisfy the universal approximation property and possess strong regularity that enables a dimension-independent generalization error. We are going to establish the following picture. So this error represents the training tree actually, and Q0 is our initialization. As we train the model on the empirical distribution, we can show that it eventually converges to the empirical distribution and suffers from memorization. However, during training, there will be a time period when the model comes very close to the true target distribution, so that if we perform early stopping, then the generalization error can escape from the curse of dimensionality. Before we present our results, let me introduce a unified framework for distribution learning. This framework will serve as the foundation of our analysis. We begin with supervised learning. It has been shown in this paper that the supervised learning model can be seen as a continuous calculus of variations problem, which is determined by 4 factors: the function representation, the training laws, the training scheme, and their discretization. For distribution learning, we have the additional factor of distribution representation, namely how we represent a distribution in terms of functions. For a concrete example, let us look at the bias potential model. Its distribution representation is given by the Boltzmann distribution, which is generated by a potential function V. And our goal is to learn this V. And next, the training loss is defined as the relative entropy, or equivalently the KL divergence, which can be written in this form. And thirdly, we need to specify the function representation of the potential function. There are several options to choose from. One option is the two-layer network, which can be written as an integral transform. One can also use residual networks, or equivalently a flow defined in this way. For simplicity, we will consider random Fisher functions, or kernel functions. They are analogous to the two-layer networks, except that we fix the first layer weights and we write them as a parameter distribution. And we also write the second layer weights by the parameter function A. So in general, those random Fisher functions satisfy the universal approximation property. We can define a norm over those functions by the RKHS norm, which is the L2 norm of the parameter function. And also, those functions enjoy a Rademacher complexity that escapes from the curse of dimensionality. So it's bounded in by this term, by this 1 over square root n rate, which is practically dimension independent. And finally, we specify the training rule. So we will perform a gradient descent on the parameter function, and it is given by this formula. We can also consider the empirical loss function Ln. So we replace the target distribution by the empirical distribution. And we denote the empirical training trajectory by ANT and QNT. So first of all, we have universal approximation theorem. We can show that if the potential functions V satisfy universal approximation property among continuous functions, then the family of probability distributions generated by those potentials also satisfies universal approximation among probability distributions. And next, we have our main results in this paper on the generalization error. So if we assume that the target distribution is given by a Boltzmann distribution with a potential function V star, then the generalization error during training measured by KL divergence is bounded by those two terms. So the first term is the training error, which is proportional to the RKHS norm of the potential function. And the second term is the generalization gap. It can be bounded linearly with a 1 over square root n rate. As a corollary, if we take early stopping time interval on this order, then the generalization error is on the order of 1 over the fourth root of n, and therefore escapes from the curse of dimensionality. So the mechanism for this generalization ability lies in our choice of the function representation. So heuristically, if we consider the gap between the population loss landscape and the empirical loss landscape, and we take the variational gradient in the function's parameters, then we get this term. So the first term is simply q star minus q star n, which is the simpleton gap. And the second term comes from our function representation. So we can show that this term is bounded by the Rademacher complexity of our function, and therefore scales as 1 over square root n. So it follows that the two trajectories, the population loss trajectory and the empirical loss trajectory, remain very close with the t over square root n rate. Here's an illustration of the training process. So the population loss trajectory converges head-on to the target potential's parameter function, whereas the empirical loss trajectory stays very close to the population loss trajectory in the beginning, and it only diverges very slowly to infinity, and the divergence is on the rate of 1 over square root n. Okay, so finally, we show memorization. So if we assume that the population loss trajectory has some weak limits, then this limit point must be the empirical distribution. And meanwhile, the generalization error always blows up, so the K divergence and the functional norm both go to infinity. So it shows that despite that we have good generalization error during early stopping, this model eventually would suffer from memorization and the curse of dimensionality in the long term. And here is a numerical demonstration. On the left, we have the early stopping solution, and on the right, we have memorization. So our model distribution's density function concentrates around those simple points. So finally, we remark on the difference between supervised learning and distribution learning. Typically, a supervised learning model such as kernel regression can achieve a generalization error on the order of 1 over square root n, which is better than the 1 over fourth root of n raised of the biased potential model. The difference is due to the following. For supervised learning, we are allowed to train the model to a global minimizer. That is, when our function interpolates all the labels. In this process, the function norm of our model is always bounded by the norm of the target function. For distribution learning, however, the global minimum corresponds to memorization. And when the model is trained towards memorization, the distribution concentrates around the sample points, and the functional norm always blows up. This difference in the functional norm manifests in the generalization gap, as we can see here, and eventually it affects the generalization error. Okay, so in summary, our contribution is the following. Our results reconciles the apparent contradiction between good generalization and memorization. Effectively, those two processes occur on two disparate timescales, so that if we use early stopping, then we can achieve a dimension-independent generalization error. The mechanism behind this generalization error lies in the complexity of the function representation. So if this complexity overcomes the curse of dimensionality, then the two loss landscapes, so the empirical loss landscape and the population loss landscape, will be very close, and therefore the training trajectory over those landscapes will also be very close. The implication to distribution learning in general is that a good choice of function representation can bias the training process toward good generalization. And in particular, for the GAN model, one can expect that its generalization error is given by the function representation of both its generator and the discriminator. For more details, you are encouraged to look at our new paper on the analysis of the GAN model. Okay, so this is the end of our lecture. Thank you for listening.